Let's start. Again, hello to everyone and welcome. So do you know what is the energy consumption of a 1-hour session of the networking channel? Or what is the carbon footprint of a 1-hour session of the networking channel? This type of question is currently hotly debated. I can just refer to the SHIFT project as one example. Should we care about those questions, and what are the research challenges? So this is a type of question that we are going to address today. I'm very pleased to introduce the 4 panelists. So we have today Raffaele Bruno. He's a senior researcher at the Institute for Informatics and Telematics of the CNR, the National Research Council in Italy. Then we have Yuri Demchenko. He's a professor with the University of Amsterdam. Then we have Tian. She is an associate professor, Worcester Polytechnic Institute. And finally, we have Gergely Sipos. He is the head of services, solutions, and support department at the EGI Foundation. So again, I'm sure that we're going to have very nice presentations about those topics. And I will now hand over to Raffaele with the first in line. Raffaele, the floor is yours. We can see your presentation. Everything is fine.
Yes. Okay. Thanks, Serge, and welcome to everybody who is connected to this panel. In my brief talk, I would like to touch upon some of the research challenges that we have to face, but also some of the research opportunities that we have when we try to make more sustainable, more energy efficient, the next generation of mobile networks. So let me start with some backgrounds. Why is energy so important for mobile networks operators? So important because today, from 20% up to 40% of the telecoms company's OPEX is due to the electricity bill. Although 5G equipment is expected to be much more efficient than 4G equipment, up to 90% more energy efficient, it's also true that we expect to have the energy consumption of 5G networks from 4 to 5 times the energy consumption of equivalent 4G networks. And there are many reasons for this. One of the reasons is clearly that the huge increase in density and in traffic will negate the savings that are due to a more efficient hardware. But also there are other reasons. One of the most important is that 5G and post-5G systems will embed edge compute infrastructure. And so the applications that are executed at the edge of the networks will contribute to significantly to the energy consumption of the 5G and post-5G systems. But also the network softwareizations and virtualization might have a huge impact on the energy efficiency of post-5G systems. And let me further elaborate on this last statement with some historical perspective. So if we consider the previous generation of mobile networks, they were built using specialized hardware. So in this case, the energy efficiency can be easily measured as the ratio between the network capacity and the energy consumptions. In this case, we have just 2 approaches to improve the energy efficiency. One is to over-provision the network. And indeed, historically, the past generation of mobile networks were planned and dimensioned to deal with the peak demand. The other approach was basically to have energy-efficient hardware design. But in this case, what we have is that the network resources are most of the time underutilized and therefore are operating in low power modes. With network softwareization and virtualization technologies, this is not anymore the case. Why? Because the network functions and the application services can be scaled horizontally following the traffic. In principle, this should be a greener approach, but in mobile networks, this is not the case. And the main reason is that now network resources, servers, are used more than in the past. And so they can operate in regimes that are potentially more power hungry. The second reason is that general purpose hardware is now used to run operator networks that is less energy efficient than specialized hardware. And there are already some preliminary results that are showing how virtualized base stations can consume much more than traditional hardware-based base stations. So this is clear that energy efficiency is a critical issue in the core networks and in general for the 5G and post-5G systems. And there are a lot of research initiatives, research programs that are specifically looking at this. In the next 5 minutes, I would like to share with you some of the research ideas that are currently under development in one of these research projects that is called 6Green. 6Green started this year, in January, and has been funded by the European SNS joint undertaking with the specific goal to study solutions to improve the energy efficiency across the whole value chain of post-5G systems. So to enable both networks, but also application running on top of these networks to be more energy efficient. How to achieve these goals? Basically, by taking advantage of 3 key technology enablers that with a nice wording has been identified, classified in the project like green elasticity, edge agility, and energy-aware observability. Let me spend just 1 minute to explain these concepts. So what is green elasticity? Green elasticity comes from the observations that in our networks, in our mobile networks, are increasingly more deployed hardware accelerators. So what are hardware accelerators? Are devices with purpose-built processors that are optimized for running specific data processing functions or workloads. One nice feature of these hardware accelerator engines is that they exhibit a very low dependency between energy consumption and the workload. In this figure, there is a nice result that is provided by NVIDIA, who has measured the power consumption of running an open virtual switch on a general purpose CPU or on a Bluefield DPU. What they were saving, not only a significant reductions on the total energy consumption, but also flat behavior of the DPU. So it means that the energy consumption, it doesn't depend really on the workload. So this is provides a huge potential for energy optimization, so because we can design mechanisms to scale vertically the network services and the application services between software elaborations and hardware acceleration. So in order to trade off between performance, between cost, and between energy, so that we have basically distribution of the end-to-end latency budget of applications between these different technologies. The other key enabler will be edge agility. So edge agility can be defined as a sort of handover procedures for workloads that would allow to provide horizontal scalability to vertical applications, but mostly to the network slices over which these applications are running across the network edge and cloud continuum of the system. So basically, here the idea is that while in data centers, the workload is basically confined in one premises, in a mobile network, the workload will be geographically distributed, will be highly dynamic. And so what we have is design mechanisms that will allow the workload redistribution based on events that are generated by the users or by the infrastructure itself, like for instance, mobility, in order to opportunistically move the latency and the energy cost between connectivity and computing. So the idea is that with edge agility, we can provide really to the system the ability to scale to zero services portion of the networks in area where those services are not used, and to be able also to quickly resume these services whenever it's needed. Finally, we have energy-aware observability. What does it mean? We know that energy accounting is fundamental for optimizing power provisioning. The problem is that if we consider the network function virtualization infrastructure platforms that are available today, they are really able to measure energy consumption at the level of individual compute nodes. But it's very difficult, if not impossible, to measure energy consumed by individual virtual network functions. There are some partial solutions for data centers where there are power models that allow to estimate the energy consumption in individual containers, for instance. But we need something more within the observability mechanisms and analytics that will allow to basically compute the energy consumption on a per slice and per vertical applications. So we need mechanisms to basically collect energy consumption metrics at the hardware level, and then combine these metrics to really understand what is the contribution of a single tenant, of a single application, of a single virtualized network on the energy consumption of the whole system. And this is really needed to move towards a green economy, where we pass from the classical service level agreement to a more complex decarbonization level agreement, where basically the energy becomes a business metric in the contract between the users and the service providers. So to conclude my talk, I will just list my takeaway messages. So the first one is network softwareizations is transforming in a radical way the way we plan and operate the networks. RAN is still the major energy consumer in the mobile networks, but the core is also relevant, and its relevance is increasing due to the edge computing, due to the network softwareization and virtualization technologies. Ways to increase energy efficiency with the core will be mainly by leveraging the availability of heterogeneous hardware accelerators that now we have, and also by designing more intelligent mechanisms to dynamically reconfigure slices applications to adjust to the workload distributions. And finally, by providing the networks with energy accountability, with observability mechanisms in order to allow power optimizations on a per individual tenants, on a per individual virtual slice and application. So thank you. And I basically finished my presentations with this.
Thank you, Raffaele, for sharing your thought with us. Be happy now to hand over to Yuri. Yuri, the floor is yours. You can start sharing. And
Yes,
again, please do not hesitate to start asking questions or sharing your comments through the Q&A.
Okay, it was my pleasure to listen Raffaele's presentation, because it provides a quite good introduction to what I was like to talk in my presentation, in my introduction, that Raffaele described extremely complex measures that are taken for make the 6G and radio access network green and sustainable and possibly this decarbonized. But is it enough? Because it's only one part of the puzzle. We need also to look at a more general approach. For example, we are doing, digital infrastructure is designed for customers. We are doing our digital research infrastructure for researchers. Is it sufficient only to make one part of this, the whole infrastructure component? I think it's not sufficient, and this is what I would introduce in my presentation, also referring to the new project that will be run since the next year, that there are many other aspects that we need to address to achieve the more general approach to greening and to the reducing energy impact and energy efficiency and the environment impact. So we can look at these three aspects of greening. First is energy efficiency. It's clear. We reduce energy. We reduce energy in all components of infrastructure. First of all, data centers. Next, it's access network and so on. Decarbonization. And this mostly related energy efficiency in digital infrastructure is to design, deployment, and making the right decision and using good hardware. If we talk about decarbonization, this mostly impact is done at the operational stage, because green energy shift in using for digital infrastructure will impact so-called decarbonization. And finally, if we talk about reducing energy impact of digital infrastructure, this means that we need to talk about the whole life cycle of digital infrastructure, starting from design and to the deployment, selection of equipment and so on. There is a lot of publication on this topic. I tried to slightly extract the most essential issues that we can put for today's discussion. And this looks like this. So if we need to talk about sustainable green IT and research infrastructure, we need actually to think about the whole ecosystem optimization, including all components and also including ecosystem life cycle, or in our case, green IT and research infrastructure. Sustainable IT refers to integration of environmental consideration into all phases of starting from manufacturing, use, disposal, IT technology, and product. And this may include the following a few group of factors. First is software sustainability. This is not actually commonly accepted, that even radio network currently is very much dependent on the softwareization, and what is Raffaele actually mentioned. So efficient coding practice will also make not only optimize the operation of the components, but also use less computational power. Commonly accepted is that cloud-based services can reduce energy, but another way, how much is efficient using fully online services to the local services. It's also issue about edge cloud, say sharing the workload. And in one of our experiments, we estimated how much energy is cost to edit the documents locally on your laptop, and how many energy it will require for editing on the Google Doc or online, say, office. And this is still not decisive condition, because you have some kind of background use of energy on your laptop if you do the local operations, but then you connect to the a remote cloud-based application, you need to increase energy up to 50% to connect for short time, and so on. So energy efficiency is another part of the whole ecosystem optimization for a sustainable and say decarbonization and environmental impact. Next is as I mentioned in the previous slide, that's reducing carbon footprint means also what kind of equipment we do, what kind of say resources we use, including for data center is also water, heat dissipation, and so on. And also what kind of how we will use the resources, what kind of equipment, and at the end of life cycle, how we can do the recycling. So this is so-called e-waste. We all know that when we buy modern equipment, TV set or whatever, we actually pay for recycling. This is hidden in data centers, but we need also to think about this. So if you talk about the full cycle of energy efficiency and decreased environmental impact, we need to also include into our discussion and our development. And finally is awareness, green practices, education and training. Importance of this is confirmed by the fact that European Commission is published Green Competence Framework for researchers that actually define what kind of competences the researchers need to have to be aware about modern technologies. And if you look about the whole life cycle of data life cycle or research life cycle, we see that researchers start from experimenting, data collection, data analysis, data archiving, and this also creates some kind of impact this life cycle of research, life cycle of data, and at each stage there are different aspects of how we can address this. So we try to research this and provide as a general architecture, general model. So here is in the upper part is the data workflow, data lifecycle, and how are other components of the ecosystem or infrastructure are connected to this. This is network. All data processing and workflow require communication. Storage. Everything stage need to be stored and actually communicated to the storage. And next, all activity can be located in different, zones of infrastructure, including sensor network, radio access network, far edge, near edge, cloud, data center, and storage for long-term storage that can be located in cloud, but also in other aspects. So all these aspects are needed to be considered, included in the model, and we will try to do this happily to have a project, Green Digit, that will start next year. And we will try to address multiple aspects of this, to build the whole picture of the energy efficiency for research infrastructures and for environmental impact reducing. So it will include like assess status and trends among the partner digital infrastructure, provide reference architecture and design principle, include the develop the model that would refer to this kind of complexity, and also develop tools that can be implemented and used for energy reduction in data centers, and surely educate and support digital service providers and researchers. For this, we will provide, expect to provide tools that will make a researcher aware and control it of the environmental impact of their developments. And project will start in half a year, but we already started so-called Green Digit Initiative, and this targets for two activities like research infrastructure survey. So we will be collecting, say, participating in infrastructures and somebody who interested, and also embedded sustainable aspect in higher education curriculum. So slides will be shared, and you can actually use this kind of links to subscribe to the our initiative activities. So this is final my slides, and I will surely.
Thank you, Yuri, for this presentation and this new initiative, Green Digit, from the European Commission. I will now hand over to Tian. Tian, the floor is yours.
All right. Can you see my screen?
Yes, it's perfect, Tian.
Awesome. Yeah, thank you so much for having me. Yeah, today I'm going to talk a little bit about our work on building the sustainable cloud and edge for emerging workloads. This is the work supported by National Science Foundation from the US, as well as VMware Research. So the big vision we have, so by the way, this is a project with a collaboration with UMass Amherst as well as Caltech. Right, so the big picture vision we have here is depicted on the left side here. So what we envision is, if you look at the current cloud, right, so we have a pretty good understanding of how to actually virtualize hardware resources by providing things like virtual machine and containers. But on the other hand, right, so we don't really have some abstractions for energy, right? So the big idea here is that what if we could actually virtualize energies, and we could then allow applications, right, running in the data centers and the edge to have more visibility and control over different sources of the energy as well as their composition. And just like they're controlling your hardware virtual devices, virtual resources, right? And at the same time, right, so you kind of have the same, a different type of the cloud and edge with different type of power resources like the traditional electricity grid, as well as some local energy systems that power by things like solar, as well as wind and hydro. Right. So the key idea here is that, with the energy virtualization, right, so perhaps we will be able to have an end-to-end approach that could delegate the resource management to the application itself, right? So then they can be more carbon and energy aware. Okay, right. So let me try to step back from the vision and trying to convince you why that might be a right approach for redesigning the cloud and edge, right? So the first observation we made is that when we look at today's cloud and data center, what we have seen is that the cloud is already operating at a very good energy efficient. So if you kind of look at the diagram on the right side, the power PUE, the power usage effectiveness matrix, which is a commonly used metrics for measuring the energy efficiency for data center, has already plateaued around 2020-ish, right? So the trend probably is going to stay there. So there's not much we could potentially do in order to further reduce the PUE. So basically the lower the better. So 1 is the optimal in this case, right? However, right, so if you think about that, right, so the cloud resources and cloud themselves at the same time is growing exponentially with new GPU servers and every type of location being open for data centers, right? So aggregately, right, we're looking at the situation that perhaps energy efficiency will not be able to mitigate the overall energy growth of the cloud data centers. Right, so that means fewer opportunities are left if we were only looking at energy efficiency. All right, right. So having said that, right, so what should we do about that, right? So if we think about energy efficiency not being the only solution, and we step back and look at different type of data centers, energy sources, you can kind of look at, there are 2 different extreme cases. On the right side here, we're giving the example of you could have any sort of data centers that operated very energy inefficient, right? So for example, this is a local site in Massachusetts. So it's Mass 0. So basically the micro data center, which is powered entirely using solar panels, right? So they are very energy inefficient. However, they are very carbon efficient because they're not using any brown energy, for example, right? On the right side, you could have a data center, they are completely optimized for the energy efficiency, but they do not really care about where the energy comes from, right? They could have a very carbon inefficient operations, right? So that said, right, so if we cannot further optimize the energy usage, but on the fortunate side, right, we also think that energy usage is not the entire problem, right? Because, right, so if we could simply reduce the carbon consumption, we could still have a very sustainable data center cloud operations, right? So the key takeaway here is that we think that when we are trying to design and operating data centers, we should not just looking at the energy efficiency, but we should also consider carbon efficiency, which is the computation per unit carbon emitted, right, when we're trying to operate it. Right. Okay, so having said that, right, so this project, what we propose is the carbon first approach to design the clouds, right? So essentially the key foundation idea is the virtualized energy hypervisor idea. So that particular work has been published in S+ 2022, right? So basically with that foundation, right, so you'll be able to give application some visibility and control of the energy they consume, right? So therefore, right, you could also potentially provide carbon information for every energy joule that is being consumed. Right, so the key idea here is that if we would treat carbon as a first-class design metric or design principle, we could hopefully achieve better carbon efficiency, right, rather than just going for energy efficiency. Okay, right. So the problem is, right, so the key idea is simple, but there are many challenges you actually need to implement this idea. I'm just going to give you one very high level challenges here, which is if you look at the data centers application, we're seeing the very diverse applications they are running in today's data centers, edge in the cloud, right? And traditionally, we're using power grid to power those diverse applications. So those has the abstraction of energy of being very continuous as well as very reliable, right? So there's no much thing that need to be done in order to mask the value, right? However, if you were to use green energies in this case, for example, solar energies, you kind of have the very messy power supplies, right? So this graph shows that the power profiles for different part of the world at different time of the day could be very highly variable. Having said that, right? So if you don't know that the green energy power profile has this type of characteristic, right? Meaning there's no visibility, it's really hard for application to adapt themselves to use green energy. And at the same time, if you don't know the variability, right? So this is very hard to have the control in terms of how much carbon they're willing to trade off for a performance, right? So that's kind of the high level challenges. But, right, so I think even given these challenges, we can still do a lot of things from the application perspective. For the remaining couple minutes, I'm going to share with you some of the preliminary work we did, which is if you kind of just think from the application-specific optimization for carbon, you could actually do much better than being carbon unaware, right? So, but from there, we can probably go much further. Here, I'm going to take the very energy intensive application called neural architecture search as an example, and to demonstrate that if you actually be carbon aware, meaning that if you can have the carbon and energy signal from the virtual hypervisor, you could potentially reduce their carbon consumption and at the same time does not sacrifice too much of the performance metric in this case, right? So briefly, if you don't know NAS, but NAS is a type of deep learning workflow that requires you to train many different deep learning networks, right? So for training them as well as you have to actually train them from scratch to using search algorithm to find the best architecture. So this is one way to automatically find a good neural networks for different workload, right? The opportunities here is if you look from the applications perspective, is that not all NAS steps are equally energy consuming. Therefore, you can do differential treatment for different steps, right? And then also there are many different strategies coming out from the machine learning community that can also have different energy requirement, which you can selectively use based on the carbon emission status at a given point of the time, right? So given those opportunity, right? So our key idea in this preliminary work is that we could use different type of GPU resources at different point of time, depending on the carbon emission status to run this NAS pipeline. So by doing so, we were able to reduce the carbon to the lowest compared to traditional approach, while still have the good performance in terms of the accuracy, the architecture found, right? So with that, I'm going to yield the floor. Thank you very much.
Thanks a lot, Tian, for this very informative presentation about how you plan or how you are addressing this problem. And so we are moving now to our last panelist, Gergely. So the floor is yours.
Thank you very much. And thank you for the previous presenters. It was indeed very informative. Let me bring in a slightly different idea, which actually can integrate some of the points that you've heard before. I'm Gergely Sipos, working for the EGI Foundation, which is the coordinator of a pan-European global e-infrastructure. And this e-infrastructure is an operational system since 2010, roughly, when it was established as a spin-off from the compute science grid that was initially built for the Large Hadron Collider. And in the last 13 years or so, we made this infrastructure a multidisciplinary, multi-technology infrastructure, integrating not just high-throughput compute clusters, but also emerging cloud systems, container systems, storage systems, and other types of services that are required for data-intensive sciences. So over these years, we built this into a production system that is now underpinning large-scale scientific experiments across the whole disciplinary spectrum, from physics to astrophysics to earth sciences, environmental sciences, even emerging fields in, for example, in humanities. And the system itself is a very distributed system. You can see here on this slide on the right side that fundamentally the data centers are federated mostly from Europe, but we have partnerships all around the globe. Universities, research centers operating high-throughput clusters, operating cloud resources are federated into the system and harmonized behind a well-defined service portfolio that is exposed to the user communities, these large-scale scientific projects and long-term research infrastructures. This very diverse picture indicates that there are different forces playing both on the investments that goes into the build-up of the hardware and into the operation and the consumption of those resources over the years. So we have various challenges when we want to lower or even measure the environmental impact of this huge system. But we believe that lowering this environmental impact of scientific computing is both a societal and ethical responsibility, but we have to do it without jeopardizing the scientific excellence that those systems are delivering today. So what we did in the last 2 years, roughly, or nearly 2 years now, with the colleagues in the EGI Federation, we run a task force inside the EGIA's European Commission project, which looked into the green computing situation of the infrastructure to better understand what are the practices, metrics, policies, or even roles within the centers that are federated, how they are considering or how much they are considering the green computing aspect and the environmental impact of their operation. We also looked into how the software running on top of those resources are considering the efficiency aspect, similar to how we heard about this earlier. Based on the findings, we defined an action plan earlier this year, which, gladly speaking, ended up in this new proposal or project, the Green Digit, that Yuri briefly presented. And we will run this Green Digit project from next year for 3 years in collaboration with the Slices, the So Big Data, and eBrains infrastructure. And the EGI perspective of that project is really to understand the opportunities and implement the low-hanging fruits to lower the environmental impact of scientific computing, considering this very complex and established landscape of the EGI Federation. So the main 4 actions that we foresee here for EGI or relevant for EGI is, first of all, to capture and spread those good practices that already exist within the centers, not just within the EGI Federation, but also within those scientific projects that are relying on EGI and extend our capabilities with their domain-specific infrastructures or research infrastructures. The second activity is about establishing a functional and operational reporting framework for the resource providers so we can bring together the knowledge about their impact, whether it's energy impact or greenness or any other aspect or carbon impact, as we heard earlier. And by bringing those data together, then we can take that data, integrate it, combine it, and bring it to the right decision makers. And one decision maker can be the user or the user community when they decide about which resources they tap into and use and how they use it. So simply by raising awareness within the user communities about the environmental impact of their workloads, whether it's a workflow or a pipeline or a scientific gateway, is already a good step towards the right direction. And we can take it further from there and making the infrastructure more clever, more environmental aware, and offering alternative solutions for the users and for the applications running there in order to lower the impact of their workload. And within the project, we foresee to use new applications or new application logic for resource selection. So then the workflows or pipelines can choose the lowest environmental impact sites within this huge federation. We can consider smart job scheduling algorithms that can delay the operation of a job or running of a job to periods when the energy coming from the power grid is greener, for example. And we can do some improvements to the software itself in order to have a better trade-off between when to compute, when to store data, on which platform to store data, considering again the overall energy or other environmental impact of this. So we are looking forward to this new endeavor with our colleagues in Green Digit to implement this action line. Thank you.
Thank you, Gergely. Thanks to everyone for not exceeding your time budget. So we are going now to move into the questions. I would like all the panelists to address the questions, if possible. I will start maybe with one very specific question. I guess it's for Tian. There was a question related to your presentation. How was the carbon measured? How did you measure the CO2?
Oh yeah, so that's a great question. Right now, we are using third-party services that's called Electricity Map, as well as Watt Time. So those are the company that work with the grid, energy provider, and then the grid to figure out that for each kilowatt hour, you know, what does those energy come from? So they're reporting those carbon emission in real time, and then we have access to their data. So if you're interested in, you can check those services out and trying to see, you know, you can get some free, you know, data from there as well. Yeah, they're pretty supportive of academia research. Yeah, thank you.
Thank you. Actually, there is a similar question. I don't know whether you would like to maybe specify. Could you tell us more about a way to measure the energy consumed and carbon emitted by software?
Right. Yeah, so I'm trying to think. So I think right now energy consumption will be easy to measure, right? Because there are a lot of things in place currently, even in data centers, to measure, you know, what is the power consumption of the, not just the computation unit, like, you know, the fan and AC and so forth. So they have industry, this type of industry have the incentive to actually do accountings. Right. For the software part, right? So depends on what kind of hardware you're running on, right? So for example, if we're talking about GPU workload, right? So NVIDIA have some tool sets you can use to measure, you know, how much energy is being used by the GPU. However, the trick here is that there's not really an easy way to account energy for different applications that run on the same hardware devices, right? So application level profiling is tricky. So that's why, you know, one of the project that I mentioned earlier that UMass Amherst did is that they want to be able to do the energy control as well as profiling at a per application level, so that you can give each application their own accountability to say, oh, how much I use, not just aggregately how much the hardware use. So I would say that's a hard question. I don't really know the full answer to that. So I only know the currently, and this is how it's being done. So carbon is as well as for the carbon, right now what we use is still the services I talked about. Thank you.
Thank you. I'm happy to see that there are a lot of questions.
Can I follow up?
Yeah, Raffaele, you want to address this one too?
Just to follow up on this, on the comments from Tian. It's very, very hard to be able to measure the per application energy consumption. And one of the really the complexities coming from the fact that there are many resources that are shared. Let's think, for instance, to a shared storage space where different applications are accessing. And it's very difficult to partition the contribution of different applications on the energy that is consumed by these shared resources or shared services. This is very relevant in communication networks, where we have services in the core networks that are basically shared by different data planes, by different virtualized network slices, and how to split the usage of this shared service between the different virtualized slices that are running the networks is very difficult. And probably what we need are benchmarks. So a set of scenarios where we can basically derive from measurements and then use these benchmarks to try to extract models for computing these different per application energy consumption.
Okay, thank you. I see really many questions popping up, especially related to the softwareization aspect, but I would like maybe to take those two questions from David Oran, because there are some elephants in the room. So he is asking whether machine learning and LLMs training are going to dwarf all those efforts. So big consumers. So a silent room means you agree, or? And I can maybe throw you the second one, which is maybe somehow addressing the digital sobriety. Is there a chance of getting the cryptocurrency miners to pay attention to any of this?
Okay, let me about LLM mentioning. Yes, indeed, the question everybody always, probably everybody was thought how much was cost energy to training the current ChatGPT new language model that, as they told, they was running a couple of months. But it also not surprisingly that almost all big companies also started training their big language model, large language models. So this is issue, but okay, training is the one part, the most energy consumption, but after that, using this is with also require infrastructure to have quick access to quickly serve users. So I don't have an answer for this question, but I know that it will be issue this this making the general impact of new technologies on environment and carbon impact.
Okay, yeah, that's a quite complex question. Maybe I can bundle those two.
Sorry, just if I can add one point, is that
okay.
More than a technical, I think that more than a technical answer, here we need really a political and economical answer. So it's clear that these huge models are going to be very energy hungry and very energy consuming. So we might, I think about what are the incentives for those companies to try to reduce their energy consumption and their energy footprint. Probably when I was mentioning this idea of having decarbonization level agreement, it's clear that if we introduce some energy caps on what these service providers are allowed to consume, then that will be a big incentive for them to try to make their systems more energy efficient. It's really not, I would say that the technical aspect is, in this case, is a little bit less relevant than the policy dimension.
Okay, thank you, Tian. I see that you are answering Benoit's question, but I guess you have to answer to everyone. Otherwise, I believe we will not see it. Two questions that I will bundle, quite general questions. So I don't know whether you can provide a short answer. So one is, what is the best energy efficiency metric for communication networks? And the second one is, what is the best way to reduce the energy consumption of communication networks? So one is the metric, and the other one is how can you reduce? What is the best way? Is there one specific aspect that you believe is must have?
Okay, so regarding the metric, I think that it's a very, very hard question, because basically there are many metrics that have been proposed for the energy efficiency, but the problem that I see here is that most of these metrics are really based on an old vision of the networks, in the sense, okay, the network is a big pipe that must provide high throughput, so the energy efficiency is measured in terms of how much energy I'm consuming to provide this throughput, to provide this capacity. But I think that the perspective should be changed, because now we are seeing a lot of real-time services. So really, the energy efficiency metric should take into consideration what is the goal of the specific service that we have to provide, because then it might be relevant to measure the energy in terms, for instance, of the latency for the or the jitter that we are able to provide to that applications. So there is not a single answer to that questions, because it really depends. We need to have customized definitions of the energy efficiency. So just there is not one single definition that fits all different scenarios. Then what are which is the best approach to ensure energy efficiency in a communication network? Okay, there are many different approaches, but I would say that I have to choose one is switching off resources. So nothing can provide a better energy efficiency than switching off something. So I think that one of the main goal of workload redistributions is actually to try to move away workload from where it's not really needed, in order to switch off parts of the networks, parts of the services, because this is probably the actions that will ensure the higher impact on the energy consumptions.
Thank you, Raffaele. Anyone else on this one? Can I move to another question? So there is this question, which is, I guess isolation is the typical approach to map energy consumption to each application. I think Raffaele mentioned that cloud data centers do it at the container level. Could you please confirm?
I told the partial solution exists. There are even tools that are basically claiming that are able to basically give some estimate. So those are not real measurements on the systems. They are basically estimate on what would be the energy consumption of the specific container, but those estimates again are based on power models. So basically they have some benchmarks that are running, and based on those benchmarks, they are trying to estimate what would be the consumption of a container with some specific characteristics, and then they are applying those power models to similar configurations. So again, those tools are, I would say that are preliminary steps towards finding solutions, and the approach that they are using, I think that is quite reasonable. Try to have a sort of benchmarks that are used to probe the systems, and so to create power models that are specific for those systems, and then to use these power models to give an estimate of energy consumption for individual software components of the system.
Thank you, Raffaele. There is quite many questions about the software dimension, so I'll push this one. Software is one of the contributors to the power consumption. Quality of the software is essential to maximize the usage of resources like CPU, RAM, and so on. Which green software practices have been identified and suggested to reduce the power consumption? Are there some good practices otherwise for reducing the energy consumption for the softwareization part? Who would like to take that one? No inspiration?
I guess I can say a few words. I think so. Again, back to the whole, how do we know how much power? How do we optimize? Really comes down to knowing how much power each component is used, right? So, like Raffaele already said, right, it's a very difficult problem, and then there's a lot of interest in academia to trying to figure out very fine-grained way to identify not just for each application, but also for each functions, right? So each line of the code, how much energy is being utilized, right? So assuming that you have this powerful tool that can say, well, when you write this particular application, right? So 80% of your energy was consumed by this 2 line of code, then you have a target for reducing the energy consumption by just optimizing how you do this 2 lines of code functions, right? So I think that's probably, in my opinion, the first step. You really need to have a tool set to be able to monitor and profile at the very fine grain. So if you're interested in, there are some interesting work at the mobile community that use system calls as a basic foundation to trace those energy, right? And then other than that, I don't know. Yeah.
Thank you, Tian. So maybe a last question from me. Many of you have addressed how we can optimize, so to speak, the cloud. But I would like to quote here Luc Julia, who is the inventor of the Apple Siri. He said the cloud is an environmental aberration. Because basically I can switch off switch on the light in my desk through the cloud. That's not optimized, right? The fact that you have a very highly centralized infrastructure. So meaning that basically you have to revise the way this has been designed towards efficiency, because you have to balance, as you said, efficiency with energy consumption or carbon footprint. You all seem to agree with this. Excellent.
Yes.
Okay, so
this is
thanks
why
a lot.
native is becoming very important, Serge.
Yeah.
That's why the edge is becoming very important, to move closer to the consumers, everything, all decisions.
That's right. So thanks a lot. We are now reaching the end of this session. I really would like to thank all the panelists and the audience, of course. As usual, I would like to introduce the next session. So for once, since we started 3 years ago, it won't be scheduled in 2 weeks from now, but in 3 weeks from now, in order to avoid November 1st. So for those who are faithful to the networking channel, maybe you remember that 2 weeks ago, we had a very interesting session, which was about lessons learned from 40+ years of the internet. But it was an academic perspective. So we would like to rebalance with an industry perspective. And so on November 8th, same time, same place. So we'll be very pleased to have this session related to lessons learned, but with, as you can see here, panelists from industry. And it will be interesting to see whether the outcomes and feedback will echo to what we heard from academia. And this session will be organized by both Jim and Christophe. So this being said, I would like to thank you all. As you know, you can watch the replay and you can continue asking questions on the networking channel Slack. And we'll be very happy to see you again in 3 weeks from now. Take good care of you. Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you.